So today we have a very special guest, an unusual data scientist, and with colorful personality and background. Unfortunately, don't know soccer. I think we gotta put that as a requirement for data scientists in Magnimind Academy. So Oriol Nieto, he's a senior audio research engineer at Adobe Research in San Francisco. Before that, he was working in Pandora as radio and music informatics and holds PhD from Musics and Audio Research Lab of New York University. It's a really fantastic background. I'm kind of jealous. And his research focuses on topics such as music information retrieval, large-scale recommendation systems, music generation, machine learning, and audio with a special emphasis on deep architectures. And his PhD thesis is about trying to better teach computers at understanding structure of music. And he develops open source Python packages, and he plays several instruments as we discuss guitar, violin, kazoo. He sings and he screams. I hope we don't hear that now. Maybe he's a special screaming. So I won't take it long, and we would love to hear from him, as it will be quite unusual and nice presentation.
Great, thank you so much for the nice presentation, Murat. I'm gonna share my screen. I'm gonna make sure I share the audio. Okay, hopefully you see this full screen. All good?
Yes, I do.
Perfect. Great. Thank you. So yeah, my name is Oriol Nieto, and I've been at Adobe Research for 6-7 months now. And yeah, I'm really excited to be here to talk about deep embeddings and section fusion for music segmentation. But before that, I'm going to give a little bit of my background and what am I doing here. So I'm originally from Barcelona in Spain, and that's where I did my undergrad in computer science. And then after I was done, I loved music all my life, my passion for all my life. And I discovered this kind of narrow field to start applying music signals with computer science, trying to make kind of sense of them. And I did a 1-year master's at the University Pompeu Fabra in Barcelona. And that's when I got a scholarship to go to the Americas. I went to California. I did a 1-year master's in music science and technology at Stanford. And that's when I started playing with the iPhone Stanford Orchestra. It was really fun. There was like a lot of iOS development. The iPhone, that was like back in 2009. So that was exactly during my year when the iPad came out, and we were really interested in trying to use it to create like new interfaces for music. And it was a great year, really intense, of course. But after that, I got a position as a PhD student at NYU, and that's when I was more formally introduced to the field of music information retrieval or music informatics. And that's kind of my main field where I have been contributing since almost 10 years ago. When I was done with the PhD, which was actually as Murat said, sorry, about music structure analysis, which is kind of going to be the whole theme of this talk. After I was done, I found a job at Pandora. So I went coast to coast to coast. I worked for Pandora, the music streaming services. For those of you who are not in the US, it's really popular music streaming service, but it's only in the US. And that's where I actually was trying to improve the recommendations of the long tail artists, those artists that are quite undiscovered. Me as a musician, that's something very close to my heart, because even though I have several albums out there, almost nobody listens to them. So if I could actually employ the content data in order to better put these songs into places where people might actually enjoy them most using data science, that would be a big plus. And that's that was my main project when I was at Pandora. I know I was there for a long time. I had like several projects, but that's what I did. And yeah, 7 months ago, I joined Adobe. I've been in the audio research group. So we do not only research on music, but in any type of audio form, such as sound events, speech, soundscaping, any podcast audiobooks, etc., and of course, music. And yeah, my main community, as I mentioned before, is the music information retrieval, and the ISMIR is the main conference for this field, and it stands for International Society for Music Information Retrieval. And the paper that I'm gonna be discussing today, we presented it last week. That last week was the week during ISMIR, which is always an intense week, even though this year it was again virtual, but it's still like it was an intense week. But it's a lovely community of mostly musicians, but they all have a strong technical background. And it's really cool to see like all of these people making sense about the music, which is what they're really passionate about. And just, okay, last slide. I play several instruments. I like to do this kind of silly things on the stage when there are no pandemics. Hopefully we're gonna be back soon. But yeah, I play guitar, and I'm in several albums that you can check out in your favorite music streaming services, and albums from metal to Spanish rumba to Catalan indie rock. And yeah, that's what I do. I have a lot of fun doing that, and being able to transfer this into my professional life as a data scientist, as a researcher. That is makes me really, really happy. Okay, but enough of me. Now I'm going to go into the deep embeddings and section fusion for music segmentation. But since this is a talk that I'm giving to probably some people that are not related to the music information retrieval field and are not familiar with the music segmentation task of this MIR field, I'm going to spend some time framing the problem, motivating it, and at the end of the talk, I'm going to give some applications as to why this is actually so relevant, and it could potentially enhance the creativity of many people. So the problem of music segmentation, which is also known as music structure analysis, is essentially given an audio signal. So we have all the time samples here of an audio signal. The idea is to identify all of those boundaries that identify the different parts of a given song. And once we have these boundaries, we label them according to their similarity. Like in this case, we'd have like the intro is in the beginning, then the verse, then the pre-chorus, the chorus. And yeah, just let's listen to the song, and probably we're gonna have a better idea of what I'm referring to.
Those walls I built, well, baby, they're tumbling down, and they didn't even put up a fight. They didn't even make a sound. I found a way to let you in, but I never really had a doubt. Standing in the light of your halo, I got my angel now. It's like I've been awakened. Every rule I had you breaking. It's the risk that I'm taking. I ain't never gonna shut you out. Everywhere I'm looking now, I'm surrounded by your embrace.
We're very sorry to stop the Queen here in the middle of this.
Yeah, actually, I decided to change the meetup group to music meetup groups now.
I think that's gonna be a hit. I'm not sure. Anyway, we just heard this beginning, like we were in the intro, then the verse, then the pre-chorus, and now I stopped at the chorus. And what I wanted to convey here is that there are important differences in between these sections. Like in the intro, even though we have kind of the same chords, there are no vocals. Then the verse, we have the vocals kicking. So whoever annotated this, identifying this boundary here, the label of verse and intro, decided that this was important enough to create a new section for the song. Then the pre-chorus, like there's a, even though the chords are the same, there's a change in timbre. So we add like this texture of the synth going on. Beyonce is doing this different melody line. And then finally the chorus kicks in and it's kind of this epic, more loud, amazing synth going on. The drums are louder. So there's like basically differences in melody, in timbre. There could be differences in harmony in terms of the chords, etc. And whoever annotates these thinks that that's big enough for you to have a boundary there and have a different section. This is, of course, very subjective. I might not necessarily agree with this, but yeah, that's one of the main problems of music structure analysis or music segmentation, as we will talk later. So yeah, music segmentation, it's a classic music information retrieval task. The approach is actually, the first ones were presented in the inception of the field around the 90s. And it's applied both to the symbolic and audio domains. But in this talk, I'm only going to focus on the audio part. The symbolic domain would be like MIDI or sheet music representation, anything that doesn't have to operate specifically on the actual audio content. The audio content is way richer, but of course, it has so much information that it requires much more computation, but then you potentially can apply it into the real world more easily. And this problem is divided into two subproblems: the boundary detection problem and the segment labeling. So the boundary detection is identifying all of those lines that we saw before, and then the segment labeling is grouping them based on their similarity. Most approaches don't necessarily put the actual names like intro, chorus, but they say like A, B, C. And yeah, that's an area that's still quite unexplored. There are not that many papers that try to actually give a semantically meaningful name to that. So yeah, both of them are challenging, these subproblems, and they're fun, and they're getting better, but it's still quite underperforming compared to human performance. So there's a lot of potential to improve this still. And yeah, this has multiple applications for musicology, intra-track navigation, large-scale navigation of a collection, automatic DJing. We will see some specific examples at the end of the talk. Okay, and to start with, I'm going to introduce one tool that it's pretty common in music structure analysis, just to set the tone, and that's the self-similarity matrices. Self-similarity matrices, imagine that you have the input, we have the audio samples in the time domain. So usually what you do first is to obtain some sort of a spectral representation of the audio signal. And to obtain this spectral representation, you usually take the Fourier transform, but there are different types of spectral representation. In this case, this is a Mel spectrogram. And a Mel spectrogram, what we have here in the y-axis is the set of frequencies. And in the x-axis, we have the set of time frames. And in each one of these, given a frequency and a time point, we have the amount of energy that we have in the signal that would make us visually actually understand a little bit better of what the song is all about, if it's more noisy, if it's more harmonic, etc. So given this, we're already helping the system later on to make sense of what's going on in the audio domain. And that's very, very standard nowadays. Mel spectrograms are used in deep learning for music quite a lot, and that they become like the standard nowadays. So once we have this, what we do is essentially compute a pairwise distance between each frame of this Mel spectrogram. So once we compute this pairwise distance, we can have, like here on the top left, we can have the distance between the first frame and the first frame. And at the top right, we have the distance between the last frame and the first frame, right? And once we have that, we end up having a square symmetric matrix. And these distances can be the Euclidean distance, the cosine distance, the correlation distance. There are like several flavors of self-similarity matrices. And then you can further normalize these self-similarity matrices to make them more visually or add some sort of an exponentiation. But yeah, this is going to be kind of the backbone of several of the most important music segmentation algorithms out there. And the cool thing about these representations is that visually you can already see some structure of the song quite visually here. So actually, when we plot those boundaries from the ground truth, from the reference that we have, we can see that they correlate pretty well to this structure that becomes quite relevant from the self-similarity matrix. And these boundaries actually come from this data set that is open source, that it's actually open out there. It's called the Harmonics data set. And Halo by Beyonce, which is this song, is available there, and that's where I extracted the labels from. Okay, before I go into how computationally we try to extract these segments, I'm going to talk about how intuitively humans do that. And 3 different principles have been identified to do precisely that, and those are novelty or homogeneity, repetition, and regularity. And I'm going to talk about these 3 using the same example of the self-similarity matrix as the backbone or the helper to hopefully make more sense of it. So the first principle, novelty or homogeneity, is the idea that you can define a new segment when there's like a significant change in one particular audio feature when you're listening to the song, like what we listened to before, that there's no vocals in the intro, but then suddenly there's a vocal. So that is a novelty change, or you can also see it as homogeneous, like the intro doesn't have vocals, the verse has vocals, and that's homogeneous through the whole segment. So if we would have an ideal representation for this type of segments to be extracted, we would have a representation that would look like this self-similarity matrix with several blocks, right? Like we here now potentially have the vocals, and we don't have the vocals here. Here we have the synth in a particular way, and we don't have it here, right? And just going through this diagonal, we could potentially identify all of these boundaries and call it a day. The second principle is repetition, and this is kind of different. In this case, what we're looking is to identify sequences in the audio signal that actually repeat. So it's not that, like in the novelty homogeneity principle, that you can kind of go through the whole audio signal just once and identify those points of novelty or difference. But here you kind of need to go through the signal twice at least to say, oh, this repeats, so I'm going to go back, right? So you can you can think of an algorithm that is going to be big O of n squared instead of a linear algorithm. And yeah, in this case, ideally the representation would look like this stripes diagonal. Like it means that, oh, look at the verse and the pre-chorus repeats here too, and there's like a chorus here, and the post-chorus also repeats here. So this would help us. Oh, there's this part that is actually repeating again. So, oh, I know that it happened here, so I know that this is a section. And finally, the last one is regularity. And this principle is a little bit more loose. Not that the other ones are not loose, but this is kind of more loose. And in this case, is this fact that most of these segment annotations have kind of a regular length. It's very uncommon to find tracks that are gonna have 2 or 3 very long segments and then I don't know, dozens of really tiny ones. So usually when people are looking for this type of segments, are trying to find segments that are more or less of the same length. And here in this case, we could argue that whoever annotated this had the pre-chorus, the chorus, and the post-chorus. If you listen to the track, you could think, oh, maybe I could just put all of these together, and this repeats here and kind of repeats here. But this person who annotated this probably did this into three separate pre-chorus, chorus, post-chorus, because these are kind of more similar in terms of length of the previous or later segments that they annotated. So they applied, in theory, like the principle of regularity. So, okay, now that we know how to annotate these, at least as humans, let's see how computers do it. And I'm going to give a little overview of the classical approaches, then we're going to go into the more deep learning approaches on how to do that, and then I'm going to talk about the our method that we presented actually last week. Okay, so approaches to music structure analysis. The most classical and actually very effective still nowadays technique, it's the checkerboard kernel that was presented in oh my God, 21 years ago. And yeah, given the self-similarity matrix, you want to very easily convolve a checkerboard kernel across the main diagonal. The checkerboard kernel, you can think of it as a binary small kernel, which you can, there are like different flavors, but you can just think as a binary that I tries to identify like essentially those blocks that we saw before in terms of novelty and homogeneity. And what you do is to convolve it, and for each point through the main diagonal, and each point in this convolution, you can get a novelty score. And if you put all of these novelty scores together, you end up having a novelty curve. So it's really, really simple and really fast. And these peaks tend to correlate to the boundaries of the annotations that someone might think that, oh, these are the different sections of the song. And you do a peak picking algorithm here, and you're able to extract those boundaries very easily. So this technique focuses on the novelty homogeneity principle, but it only identifies the boundaries. Then it doesn't really group them based on how similar they sound. Another, this is kind of a different set of techniques, but I wanted to talk about it. We actually presented a method back in 2013. The idea is to, given a spectral representation, in this case, you can think of it as a representation that collapses all of the pitches into the 12 Western pitches of the Western scale, so 0 to 11, right? But this is still like the time domain. And the idea is to just apply matrix decomposition here, which is pretty standard and pretty easy to apply. And there are different ways of different type of flavors of music of matrix decomposition that you can apply. You can apply NMF. There's a variant of NMF called convex NMF that actually works really well. But the idea is once you select the rank of decomposition, like in this case it would be 4, you can make it such that the activation matrix is quite sparse, so that naturally the segments appear here. And you can already just extract that information and make it your output to your algorithm for the segmentation of that particular song. So imagine here, you see that the segment type number 1 would occur here, it would occur here, occur here. Segment type number 2 would occur here, here, here. You see that it naturally, just from this matrix, this activation matrix of the decomposition, you can obtain already music segmentation. This would focus on the novelty and homogeneity and repetition principles, because once you do the matrix factorization, you need to take it's like this basically EM algorithm that has to go through the entire matrix. So in a way, you are taking into account what comes after and what comes next. And this actually identifies both boundaries and labels, right? It's able to tell you, oh, this segment type is type number 1. So that's how all of these 3 are going to be similar. The other one, in terms of matrix decomposition, that I wanted to talk about is the one proposed by Weiss and Bello in 2011. I thought it was really smart. This, in fact, won the Best Paper Award in Izmir in 2011, I think. And what they do is it's pretty similar. You also get the pitch class profiles, the chromograms, like this representation that has all the pitches in the y-axis, and you decompose it. But in this case, they applied shift invariant probabilistic latent component analysis, which instead of decomposing it into 2 or 3 matrices. They can decompose it into this tensor, sparse activation, and then they convolve it with a set of weights, and then you have the sparse activation matrix, which again, that's where you can obtain the final set of representations. Here we would say like the first segment type, you can actually see that it will occur here. The second segment type, it happens here, 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 and here. And yeah, the cool thing about this approach is that it was all from a probabilistic framework. So the number of unique segment types could be defined, could be actually learned from unsupervisedly from the data. Okay, another classical approach, that's the structural features. And I just wanted to talk about it because this obtained state of the art back then. And it's so easy and it's so fast to implement that still nowadays, a lot of people use it if you don't want to deal with training models and do more like of a modern approach, which usually give better results. But this is, again, super easy to compute. It's a really interesting idea. Just a brief overview, given, again, the chromogram of each class profile, what you do is to take, they don't take the self-similarity matrix, they take recurrence plot, which is essentially a self-similarity matrix, but it's binarized with, you can have like fancy ways of just binarizing the recurrence plot. But yeah, once you have this clean recurrence plot, what they proposed was to put it into this kind of like shifted representation or rotated representation. This is a lag matrix. It's like, given a point in time here, I want to see what happened before in time, but they kind of shifted it. This is not, they proposed this kind of shift to be able to recognize the repetition parts of the signal. And once you have this representation, you can actually apply some Gaussian filter, some low pass filtering into this signal, and you just take the average across the y-axis, and you again get your novelty function where you can extract the boundaries from the peaks. And that, again, this was a state of the art for a while. This focuses on the 3 principles because you can apply some regularity here too, and this, you have the repetition, and of course once you go through this you get all this novelty, right? So this is only focusing on the boundary detection, but in their original paper they propose a separate labeling scheme for identifying the similarity between the segments too. Okay, and now we are approaching the present. And yeah, the first paper that actually used the CNN, or deep learning, for the task of boundary identification was back in 2014. And here I'm going to talk about this kind of like paper that they then did in 2015 that they kind of enhanced it. But the idea is quite simple. So as I mentioned in the beginning, these spectral representations, MEL spectrograms, are really popular for music processing with deep architectures. And the cool thing about them is that they're pretty compact. You only have here in the frequency axis, you only have between 60 and 120 frequency bins. So while, yeah, this can be in the order of hundreds, this is relatively small, so you can treat these as an image, and that's what the music informatics community has been doing. And this is kind of what we do. We see that, oh, this works in the computer vision field. Oh, this works in the NLP field. Oh, this works in you know, other fields that this seems relevant where they're applying machine learning. Oh, I'm going to try it here in music, and it usually works really well. So you treat this as an image, and then you can easily just use a CNN to try to extract something for your task. So in this case, this CNN, they train it as a boundary classifier. And I thought that was really smart because then you have the annotations with the boundaries. So imagine you have a boundary here, so you train it as a positive example of finding a boundary. And if there's not a boundary, that's a negative example. So a standard CNN classifier. And once trained, you can just go through the full one string, you can go through the full MEL spectrogram. And for each patch that you go through, you get a likelihood of having a boundary or not. And that is actually similar to a novelty score, right? So you keep going, and then on the end, you have this nice novelty score. And then you, again, apply the peak-picking algorithm to identify the boundaries. This focuses on the three principles because they not only use this as an input, they also use other representations like the lag matrix, which can encode repetition. And in fact, they use like some other techniques to make it like hierarchical. And I'm going to talk about hierarchy soon. But yeah, this was a really effective technique. This won there's like this competition every year that they won. Of course, deep learning comes and then everything is better. But yeah, this only focuses on boundary detection. Okay, and I think this is the last one that I'm going to talk about in terms of just plain boundaries or plain music segmentation or flat music segmentation, and that is contrastive laws. And contrastive laws, it's like the hot topic nowadays, or at least it is in the NLP field and now music informatics too. But it's this idea of metric learning, of learning these embedding spaces and doing them in a self-supervised way. And this is what they did. The idea is to, again, you have a CNN that you actually train as a similarity classifier. And this is really cool. I thought that Matt McCollum did this. It was really smart, because what he did is, like, if there are two frames of audio, well, in this case, MEL spectrograms, that are close to each other, what I'm going to do is to say that they are similar. They are similar in the sense that they belong to the same segment. That's going to be noisy, because that's not going to be always true, but most of the time it's going to be true. And then I'm going to use the same anchor and use the negative example of a MEL spectrogram patch that's farther away, for me to say that this is not going to be part of the same segment, which, again, it might be that it's the chorus too, but that's more unlikely than just finding a point in which it's actually a dissimilar segment. So the cool thing about this, of course, is that you can just train this with all the audio that you have in your collection. You don't need human annotations to train this, right? So what he showed is that once you do that, you end up having a really clean self-similarity matrix from which you can apply something like the checkerboard kernel to obtain the boundaries, or whatever technique that I've talked about before to obtain the final set of boundaries. And this actually, of course, again, obtains better results. And I could talk last week at Izmir, there was a technique that actually made it better. And it was really cool because they applied it to several techniques, all of this self-supervised, all of this self-supervision. And yeah, anyway, deep learning, they come and it makes everything better. And yeah, this focuses on novelty, homogeneity, and the regularity principles based on how they extract the boundaries. And this is, again, only for boundary detections. The how you apply this to the labeling of similarity, it's still not 100% clear. Okay, now I'm going to talk about hierarchy, and we're getting close to actually the method that we presented last week. And what we know is that music is inherently hierarchical, and kind of trying to annotate a song just in a flat way, just obtaining this set of boundaries, maybe it doesn't really make sense, or it might not serve the purpose of one particular application that one user might have in mind. So researchers have been trying to encode some sort of hierarchical or multi-level structure into their algorithms, or even into the data that they're gathering. So how can a music structure analysis approaches capture such structure? So this hierarchy, so as I said, some researchers started to put it in their annotations, and there's this data set called SALAMI, which is actually an acronym for structural annotations for large amounts of music information. Yeah. And yeah, this is track number 10, and this is visually their annotation for a single track. And you see that it has 3 levels of annotations, and you can think of it as a 3-level hierarchy. The function level, the coarse level, and the fine level. The function level is pretty similar to the coarse level, but basically almost only the labels are changed. So you have like these functions or semantically meaningful segments here, and you have the here usually in the coarse level you just use uppercase letters, and the fine level just lowercase letters. This is a song by The Cure. Let's listen to the first minute or so of it. Oh, sorry. Oh no. Oh no. Sorry. Well, anyway, I guess I can keep going. Okay, I just wanted to get to this part because I quite disagree with, I agree with the fine level, but then I don't agree with the coarse level. I think there's A and B are pretty similar, but then there's like a very distinct part at the end of the verse that changes like the full melody, the full harmony, the chords. So for me, that would be a completely different segment, even in the coarse level. But in any case, this is just one example in which several people might not agree with the same annotation, and that's what makes this problem really hard. And a lot of people are actually trying to work on that. But that's a different topic. What I'm gonna talk about now is some approach to hierarchical music structure annotation, music structure analysis algorithm, in which we actually based the work that we presented last week on, and that's Laplacian structural decomposition. And this is a really cool approach that was presented back in 2014. And the cool thing about this is that it yields however many different levels in the hierarchy as you want, which can be really cool for certain applications. So again, we start with the audio signal, and in this case, what they proposed was to extract the MFCCs. If you're familiar with speech processing, MFCCs are a spectral representation that focuses on timbre. It can capture timbre pretty well, and it's used especially for speech processing. It used to be. Nowadays, I think Mel spectrogram are kind of taking over. And then you take the constant Q transform, and this is a way to enhance it with harmony. So in a way, you can think of it as you have timbre and then you have harmony at the same time. And from these two representations, you take a self-similarity matrix. It's actually a recurrence plot, so it's binary. And yeah, in this case, once you have these, you merge it into this affinity matrix that can be merged using a little mu parameter that actually tunes how much relevance you're going to give to the harmony and how much relevance you're going to give to the timbre. In this case, you can think of the harmony, the chords that might repeat as the matrix of repetition. That's why it's like R rep. And the other one is like a local matrix, like they're like local changes in timbre that might occur. That are here, and that's how you actually get finally the affinity matrix. Once you have the affinity matrix, you apply a spectral clustering, so Laplacian structural decomposition, And what this will give you is a set of multi-level segmentation. And from here, you can pick whatever level you want, or you can just keep the full hierarchy. And yeah, this focuses on the three principles, and this gives us both boundaries and labels, and it also gives us the hierarchy which we're looking for. And I'm just gonna spend just 1 or 2 slides on the spectral clustering because I think it's really, really cool. So given this affinity matrix, the main idea is to treat it as a graph. And you can think of it as the adjacency matrix of the graph. And the idea is that the parts that are connected, those are going to be the ones that belong to the same segment. And the ones that are not connected are going to be in part of a different segment. And you can apply graph partition techniques to go deep into the hierarchy of this graph in order to obtain a set of a representation that then you can just partition into several different levels in the hierarchy. In this case, what you end up having, and I'm going to talk about how you actually obtain this, is a set of eigenvectors that come from the Laplacian matrix. And in this case, the second eigenvector, you can discard the first eigenvector, which means like the full graph is connected. The second eigenvector, you can see that it's all positive here and this negative here. And this makes sense because in this song, you have the very end is very different than the rest of the song. This is come together by the Beatles, by the way. And in the second, or well, I guess the third eigenvector, you can already see the structure here, that this part repeats, this part repeats, this part repeats, and you can keep going, and you can go as much as you want, as farther as you want. And how you obtain this? Well, you obtain a degree matrix of the adjacency affinity matrix. So it's basically a diagonal telling you how many points are connected to how many vertices in the matrix. And then the L is the symmetric normalized Laplacian matrix. The Laplacian formula is really simple, but here is just the symmetric normalized one. And from here, you just take the eigenvectors, and those eigenvectors are going to be the basis of spectral clustering, or where you obtain all of this final hierarchical representation from. Really cool, really smart. Just wanted to show here how yeah, if you take these eigenvectors and then you just take the similarity between them, you just take the dot product, you can get like these representations that make it visually really, really prominent, all the levels in the hierarchy, in this case up to 10. Okay, now for realsies, what did we do here, and what are we proposing? So we propose is the deep embeddings for music segmentation. I'm gonna focus on the deep embeddings part. So we based our work on this spectral clustering technique proposed back in 2014, and what we want to propose is to replace those features by deep embeddings. So we remove the timbre and we add these deep few shot embeddings, and they actually also represent timbre. So what are these deep few shot embeddings? These come from training a model not on audio. So we are in a way applying transfer learning here. And what we did was to do this for timbre similarity. And this was done by Yu Wang at the Adobe Labs one year ago. And this is very robust to noise. So the cool thing is that they learned this few shot learning in a way like this embedded space, so that you can apply few shot to just give an example that wasn't annotated in the data set to identify the similarity between it. And we just replace that. And then on top of it, we also add these deep similarity embeddings here. And these do come from a music tagging problem that also was done at Adobe a year ago and was presented last year by Jungpil Lee and others, and I think that was in ICASP, which is a speech processing and audio processing conference. And the idea is to disentangle the music similarity space such that you can actually get that embedding representation and divided it into 4 specific musical attributes: genre, mood, tempo, and era. And in the idea of these deep embeddings is that they complement the constant Q transform, the harmonic part of the system here. So these were trained, you can refer to the original papers, they were trained on different types of data sets. And once applied here, we'll see that they give us so much better results. So one kind of technical thing that we need to do is now we, instead of 2 recurrent matrices that we need to combine to get the affinity matrix, we have 3. So what we do is to kind of combine the 2 of a harmonic one into one, and then we apply the same type of weighted average to get the final one. And in this case, instead of having just one mu parameter that controls the weight, we have mu and gamma. So the gamma controls the amount of different types of harmonic representations that we want to have, either the standard harmonic from the CQT or the deep similarity, and you can of course just choose half and half. And then the mu parameter that again encodes the amount of weight to the timbre and the amount of weight to the harmonic part. I guess I had all of this here. Oops. Yeah. So once we apply all of that, we can actually see visually how different the results can be. And now here I have a hierarchical representation of one output. This is a song, "The Number of the Beast" by Iron Maiden, and here is what we actually get. And this is just applying the deep embeddings, and it's really interesting to see that for example here in the 3rd level of the vanilla, the main process that was presented a few years ago. This technique thinks that the 3rd level, there's this part that is almost always the same, except here that there's some breakdown. And this, if you listen to the song, this doesn't make that much sense, as opposed to here, our technique is able to obtain the difference between the intro and the verse. We'll hear that the intro is just speech. So it's speech, then the intro without drums and kick drums. And then it has like the kick drums that kick in here, and it's able to identify that. Then in the next level, the 4th level is able to identify like the different verse and chorus sections, and you can just go deep into the hierarchy. Let's just listen to this very quickly.
Woe to you, O earth and sea, is sick.
Alone, my mind was blank. I needed time to think, to get the memories from my mind. What did I see? Can I believe that what I saw that night was real and not just fantasy? Just what I saw in my old dreams, were they reflections of my Walkman staring back at me? 'Cause in my dreams, it's always there, the evil face that twists my mind and brings me to despair.
I'm sorry to stop this. I know that's way more interesting than my talk, but yeah, instrument part, this is just the break, but you can hear the drums here and then the drums keep going. And yeah, thanks to the deep embeddings, we're able to identify musically or acoustically all of these differences much better. And yeah, we have like this little part that is very noisy. And just objectively, when we evaluate this using the standard metrics, we see that when we apply the deep embeddings compared to the vanilla part, in all these 3 metrics, all of them are better. Now, what we want to do is, though, here it's still like very noisy and some stuff going on. So can we do it better? And yes, we can. What we can do is to apply the section fusion, which is the second part of the contribution of our proposal. So what we do is actually really simple. Once we get into this multi-level segmentation moment, we apply this very simple, very heuristic approach to apply this multi-level section fusion to obtain a much cleaner set of segments in a hierarchical way. And this focuses on the three principles, and this, of course, yields both boundaries and labels, and this yields state of the art. Like applying both deep embeddings and section fusions gets like the best scores in terms of hierarchical music segmentation. And how does this section fusion part works? I'm just gonna go through this pretty briefly. It's pretty simple. There are like 4 different types of moments that we could apply this. And the main idea is to leverage consistency in section labeling across all the segmentation levels. So you need a minimum section duration. That is a hyperparameter of the system. So once you have that, imagine that you have a section that is smaller than the minimum duration in the beginning of a segment. Well, then this is the kind of the base case. Then you just merge it you fuse it into the rest of the segment. And these are also base cases. What if it's in the end? What if it's in the middle of the same segment? Well, you just fuse it to the same segment. Okay, pretty simple. The other case is, what if it's in the middle of 2 different segments? Now we don't know which one to merge it to, right? So what we do is to go down in the hierarchy and say, is it similar to the one in yellow? Oh, yes, it is. Oh, okay. So I'm going to just merge it here, and that's where we got it. Okay. Then the next one is kind of the same, but what if we actually look down and, oh no, there's not even yellow. It's like this magenta color. So this doesn't work for us. So this doesn't work. Let's go down. Oh, okay. So this is the yellow is back again. So what I'm going to do is merge it into yellow, and that would be the result. And finally, the last rule that we designed is, okay, the same scenario. We have like 3 different types, and we go down, and oh my goodness, there's nothing going on here that we can see here to merge it to. So in this case, what we say is like, we're going to delete this segment and just create a new one, merge it to the new one that was created here. So once we apply these, we get a much cleaner representation. Look at the top thing, that there's like all of these spurious sections. We actually obtain something like that aligns much better to the ground truth. And if we do this, actually the scores are way better. And yeah, and that's actually the comparison between the original technique proposed back in 2014 and the one that we propose. Of course, this is only for one track, but the data set is evaluated across actually almost 1,000 tracks, more than 1,000 tracks. Oh, and here what we did was like a little experimentation with the mu and gamma parameters, so that depending on, we did like a grid search for 2 different data sets, and we identified different sets of parameters for both data sets. And what we show is that no matter what type of parameters you use, either you have optimized them in the harmonics data set or the salami data set, it actually works pretty well on all of them. It beats state of the art. So we were pretty happy about it. And that's our paper. And I'm not sure how much more time I have. I can talk about how to apply music segmentation algorithms. Hopefully this was the most fun part of my talk. But Murat,
we can have another 5-10 minutes.
Oh, okay. I'm gonna just go over this relatively quick. One of the main applications that I see here is this is pretty close to what I do, is to actually, if you're working on a new song that you imported to your favorite digital audio station, to actually obtain this set of structure automatically. When I work and I write a new set of lyrics and I record the vocals, I usually get the rough recording from the rest of the band, and it just looks something like this. And what I do is I do manually add all of these labels. This is in fact a real work that I did a month and a half ago. So it would be great if DAWs, the digital audio workstations out there, could actually do this automatically. Jukebox, I'm not sure if you're familiar with the amazing model called Jukebox that OpenAI put together maybe 1 year and a half or maybe 2 years ago. They can generate music in the time domain, and it's really cool, but it's still not super cohesive in terms of the structure or large long-term structure. So I think algorithms like music segmentation could help a lot in the music generation. There's this remix tool by Adobe, actually, in Audition. You should check it out because it's pretty amazing. You can, given a track, you can make it longer or shorter, and it will find times in the music that will make sense to make it shorter, such that it doesn't really make any click or anything. It makes it super natural. The video is really cool. I would recommend it, watching it. Another one, something that we presented at Adobe Max, which is this big Adobe conference a couple of weeks ago, is this find similar music. So you can actually add the music that you want to use as a query. And you can find similar music in a collection, but the cool thing is that the collection could be segmented at a section level and identify those segments that sound most similar. You have them. I thought it was pretty neat. And yeah, finally, you can apply this to video games or live performances. There's this Harmonix Music VR, which is this experience on VR that you can load a song and the whole thing, scenery, is gonna follow the beats, and it's follow this amazing colorful way of experiencing your track. But once there's a section change, the whole thing changes radically. I don't know when the chorus comes, and it's pretty epic. And I contributed to the music segmentation for Harmonix. It was a lot of fun. That was several years ago. It could be applied to Dance Central if you want to load your track and you want to have cohesive body moves during the same choruses. It's been applied to video games where the transitions in between scenery to make them like more smooth, not only aligning them to the downbeat, but also aligning it to the starting of a new section to make the transition much seamless. And finally, it could be applied to live performances. In fact, it's been applied in live performances where you can automatically adjust what's going on in terms of the section that you're in to adapt, I don't know, the video, the lights that you have there going on. And this is, for example, this band is called Meshuggah, is from Sweden, and they program their lights, and it's amazing. But maybe thanks to music structure analysis, they could have like a small template to start with, and then they can further tune, and that would probably save them a lot of time. And that's pretty much it. As a conclusion, music structure analysis, powerful you have become, but long journey ahead you have. So yeah, MSA is far from being solved. Plenty of opportunities for you to do research on it. I encourage you all to join us, to have fun together trying to work on this. Deep embeddings can help obtain better representations. Deep learning, of course, making things much more performing. And then post-processing techniques like the section fusion I discussed can further contribute to increasing performance. And just the last thing, we are hiring interns for 2022. If you're a PhD student and would love to work on something similar like that, please reach out or apply. Let me know. This is my Twitter handle, and that's my email address. And yeah, that's pretty much it. Thank you so much.
Thank you. It's a fantastic presentation. We have a lot of Q&As. If you want to just have, answer them.
Of course, yeah. Sorry, I missed all the chat with the screen like this. I can't.
Most of them is in Q&A.
Oh, I see. Cool. So I'm going to go in order. Do you see parallels between the music segmentation task and part of speech tagging in NLP? Are there transferable techniques? Oh, that's a good question. That's by Danielle Padden. And hopefully I answered a little bit in the middle of the talk, but definitely, yes, there's a lot of overlap. And in fact, we borrow a lot of techniques from NLP. And I think one of the latest trends in music informatics is to kind of follow the trend in NLP of self-supervised learning. So models like BERT, models like GLOVE, GPT-3 that are trained on so much data in a kind of self-supervised way can be put out there and then use them to fine tune a smaller model or just like an MLP on top of it to perform like downstream tasks with much more reduced set of labeled data. And definitely we take a lot of stuff from the speech tagging community. And in fact, we also contribute to that. There's the DKs right now going on, and several people of my team are working there. This is like, yeah, I think there's the paper submission is this week. Anyway, yeah, there's like a lot of overlap. Hopefully that answers the question. The second question is by HW. Mel Kepstrom work was done in the 70s through 80s. Has anything new been discovered since then? Why do wavelets not work? Oh, wow, that's a great question. And yeah, like it's pretty amazing. MFCCs have been used for music in a way that it kind of doesn't make sense. And Mel Kepstrom MFCCs were proposed by Dr. Beth Logel in the MIR community, and that was back in the 90s or no, sorry, in the I think it was the year 2000. And the first reaction was like, this doesn't make sense for music. And she was like, well, yes, but it works. So since then, it's been used in the music informatics community. Wavelets have also been used, but the results haven't been that good. And now what is happening is that MFCCs and wavelets and like more hand-tuned type of representations are not being used that much, and now you just work from a low level signal like the Mel spectrogram or just even like spectrogram, just full spectrogram, and you feed it to a model. Even just raw wave audio, like look at what the DeepMind is doing with WaveNet. They just use the actual raw audio in the time domain to feed the models, and it works really well. So yeah, I'm not an expert on wavelets, but and I'm not sure why exactly they're not working, but I know that just feeding the something like the Mel spectrogram or even just the raw waveform is actually going to give you really good results nowadays with the advent of deep learning. Okay, Amit Agarwal, sorry to probably mispronounce her name, says, do the song identification algorithms use music only or vocals only or both? Oh, that's a very, very interesting question. So actually, I don't know any works for like audio content-based music structure analysis that use the lyrics. I know that, for example, to identify cover songs in a large collection, they can use lyrics. There's a task in music informatics, which is to get like the transcriptions of the lyrics automatically if you don't have access to the real lyrics. But I don't, from the top of my head, I don't know any work that has been using the vocals. I mean, the vocals are encoded right in the full representation, but to use like in a multimodal way to try to obtain the actual lyrics in a way, or vocals and then the full rest of the signal, I haven't done that, but I think it's really interesting. It might actually work. Okay, Pau Rodriguez says, are there similarity measures between spectrograms that are relative in terms of frequencies? I'm thinking into detecting similar structures in different tonalities. It's like chord progressions. Does this exist? That is a really good point. So I would recommend taking a look at the work by Dr. Jordan Smith. He is actually working for TikTok now at ByteDance, and he's done a great work on music structure. He was the one who proposed the Salami dataset back in 2011, and what he found is that depending on what type of frequencies or what type of features you're paying attention to in the spectrogram, you might decide that there's a boundary here or not. And this is, I think this is kind of the key to solve some of the problem of the ambiguity in music structure analysis, because I would say that I would agree with a specific structure if I pay attention to one particular instrument, one particular set of frequencies you can think of, but not if I listen to another particular set of frequencies. So I think what we would need is to do like a deep, thorough analysis on these, and Jordan Smith started doing something like that. So, but yeah, it's a really good point. I think that, I don't know, there's so much to do. Okay, for the interest of time, I'm going to try to go faster. Mohid Vyas, is the kernel only applied on the diagonal to produce those peaks? Yes, only in the diagonal. That's why you can only get the novelty. You don't get the repetition principles there. Oh, what song was that? That was, I think, oh, that was 1250. I think that Mohit is talking about The Number of the Beast by Iron Maiden. HW, did music retrieval systems like Shazam work in a way similar to what you, oops, I guess people are typing and it's kind of going. Oh, sorry, I lost it. Did music retrieval system like Shazam work in a way very similar, to what you have described? The system listens to the user's humming of a song and it finds the closest one. I don't know exactly how Shazam works, but probably what they do is try to identify like an embedded space. Not sure if they use deep learning or more like handcrafted digital signal processing techniques to identify like a low-level representation that it's quite compact, that then they can like project into a space where they can identify a song that lives super close to that space. That is my guess on how these things work. And in terms of humming, query by humming, which what is it? What is the app that I know that there are apps that you can just hum or sing and they will retrieve a song. They usually focus on other types of embeddings that can do like the multimodal retrieval and do something like that. But the idea is that you try to codify whatever you're singing or the song or even like little parts of a song into that space. I'm not sure if they apply like music segmentation algorithms when they do that. Amit Agarwal asks, the recommendation application interests me, but looking at it from a different angle. If I am Spotify and I know a listener likes 100 songs, I want to predict whether that listener will like the 100th song or not. Will music structure analysis be helpful? I think in this case, I don't see a direct application. What I do see is that Spotify could potentially segment all their collections and have like some sort of an interface where a user not only says, I like this song, but goes to, I don't know, the guitar solo and goes like, I love this part. Can you give me more like this? And this is kind of where I was trying to convey with the little video that I played in terms of find similar music. And I think that would be so powerful. Like, what if I can go to a specific part of a song that I absolutely love how, I don't know, like the melodica plays with these textures going on in this kind of chord progression. I love this. I select that section that's been segmented with an MSA algorithm, and then I can get a set of songs that have sections that are really close to that. Yeah, it would be amazing. Okay, Chidam Perumal, does the section fusion involve some kind of probabilistic theories to validate which sections to join with which? No, it's all very simple. It's all rule-based, and the only tunable parameter is the minimum duration. So it's really simple. It's like, nowadays it's kind of hard to see a system that applies this set of rules and actually yields really, really great results. But I agree that this could be further enhanced by framing it under a probabilistical way. Chidam Perumal asks another question. How would you know you have segmented the track correctly? Or what metrics do you use after segmenting the track? Yeah, that's a good question, because I haven't talked about this. I didn't have time. there are several ways of evaluating objectively a track given a reference annotation, and there are many ways to do that in a flat segmentation, but also some ways to do it in a hierarchical way. And there are ways to actually just assess the boundaries, and also ways to assess the similarity between the different segments. And I don't really have time to go over them, but we wrote a tutorial on music structure analysis back then, I think back last year, so not that long ago. I think I'm still sharing the screen. Yeah, I think it's here, and yeah, it's published in the Transactions of International Society for Music Information Retrieval, and they have all the details in terms of all the evaluation metrics and all the data sets that are publicly available, and also all the problems that might induce, because if you're only comparing it to a single reference, that's going to be not ideal because of the problems of subjectivity or ambiguity that I discussed. And then Chidam Perumal asks another question. Do you recommend any readings in embeddings? Oh, yes. Okay, so just very recently, in terms of music embeddings, I can pull it up real quick. Let me see. It's here. Last week it was amazing, and Izmir is great. I love that conference so much. And I noted like my favorite 10 papers, and I have them here. And it was some of them are especially that, like a big part of the conversation nowadays is like, can we train a super large model in an unsupervised way to get embeddings that are really powerful to use somewhere else? And that work that I was trying to find was nominated to best paper, and that is called, I can type it, but it's called Codified Audio Language Modeling Learns Useful Representations for MIR. And that's by Rodrigo Castellon, Chris Donahue, and Percy Lang, some people from Stanford. And it's pretty amazing. What they did is actually use the jukebox model from OpenAI and see that it actually works so well for most of MIR techniques. And yeah, oh yeah, someone asking about making the fulls. Oh yeah, sorry. Not sure if I lose. Oh no, I still see the questions. Perfect. Yeah, so that work was really good. It was just presented last week. Look up Chris Donahue, Rodrigo Castellon, jukebox embeddings. It's really cool. Another question, keep refshare. Has someone made a music visualization package that creates a flyover animation of the graph time synced with the music? Yes, I didn't use it for this talk, but we actually used it before. It's called LSD Viz. It was developed after the authors of LSD, the Laplacian structural decomposition algorithm, put together their repo. Look up LSD Viz as visualization, and the author is Brian McPhee, which is the author of Librosa, the package of the audio processing in Python that is nowadays super popular. Look up LSD Viz, and it's this really cool circular shape, interactive way of visualizing music segmentations at different levels. Oh, and yeah, Chidam says, appreciate your patience in answering all my questions. Thanks for an awesome presentation, Oriol. Interesting. Thank you so much. And I think I went all over the answers, the questions. Yeah.
Thank you. That was a terrific presentation. I think it's a great niche topic, and you got really great engaging audience.
Oh, thank you.
For you, and appreciate the audience. And I shared our LinkedIn page on our YouTube channel. That presentation will be there if people want to just listen through that, watch it again. It'd be great. Thank you, Oriol, for your time again. Appreciate it.
Thanks for having me. That's so much fun. And I can share the slides. Also happy to give you the PDF.
Sure.
Slides too.
Thank you.
Okay. Thank you. Have a good day.
Have a good day. Bye.
Thanks.